forgot to erase these things from when I was practicing. Okay, so starting our notes on 14.3, one-sided limits, continuous functions. Again, we're just continuing what we have been learning. The only thing new is up here, determining if it's from the right or the left. The negative means coming from the left because you're coming from the negative side, that's the left side, and the plus is coming from the right side. So with this piecewise function, we're going to do like we did before and start by graphing it. Okay, so the first piece I want to do is that all of the change happens at x equals 2. So I'm going to draw a pink dotted line down x equals 2. Then I'm going to do the first piece of the function of 2x minus 1. So I'm going to put a point at negative 1 and then go up 2 over 1, up 2 over 1 until I get to that pink line and put an open circle because it's less than, x is less than 2, and then connect my points. The next piece is the equation y equals 1, but only at x equals 2. So that's the point 2 comma 1. So I'm going to put a point at 2, 1. The next piece is x minus 2, but when only x is greater than 2. So we're going to be doing this on the right side of the pink line. So down 2, put a dot, and then go up 1 over 1, up 1 over 1, and put an open circle once you get to that pink line. Keep going up 1 and over 1, so you can continue your line going the other way when x is greater than 2. So now we can determine the limit from the left and the right and what the limit is. So coming from the left side of x equals 2, once we get to that pink line, we have the y value of 3. So that's what the limit is from the left side. Now coming from the right side of x equals 2, once we get to that pink dotted line, we're at the y value of 0. So since the limit from the left and the right are not the same, the limit does not exist. Okay, so determine the numbers at which the rational function is continuous. So to do this, we want to find where the function is not continuous. So we do that by only looking at the bottom, because when the bottom equals 0, that means it's not defined. So we're going to start by factoring it. So what multiplies to 8? That adds to negative 6. And that would be negative 4 and negative 2. So the factors are x minus 4, x minus 2, and these cannot equal 0. So x minus 4 can't equal 0, and x minus 2 can't equal 0. So that means x cannot equal 4 or 2. So the function is discontinuous at both those x values. So r of x is discontinuous at x equals 4 and 2. The next piece is to find out what's happening at those x values on the function. So let's first rewrite the function with the new factors. So x minus 2 on top, and the bottom was x minus 4, x minus 2. The x minus 2's are canceled, so we're left with r of x as the limit, and we'll do the limit as x approaches 2 first, of 1 over x minus 4. Just plug in 2, so 1 over 2 minus 4 equals 1 over negative 2. So since we got an answer, that means there's a hole on the graph at 2 comma negative 1/2. So hole at 2 comma negative 1/2. So what about 4? As the limit as x approaches 4. If we plug in 4, we still get 1 over 0. So that means there's a vertical asymptote at x equals 4. So now to graph it. We're going to go ahead and put a graph down. And the first step is to put the vertical asymptote at x equals 4. And then at 2 negative 1/2, I'm going to put an open hole. From here, we can just go to our calculator to see what the graph looks like and fill in the rest. And then we're done. So this last example is another piecewise function, and we're just going to be determining the limit at where the graph changes. Only the graph changes. So where the graph changes, and that would end up being at x equals 0 and 2. So let's go ahead and plot it and see what's happening at those points. We don't want to know the endpoints, just between the differences of the different pieces of the function. So first is x squared, but only when x is less than or equal to 0. So I'm going to draw my quadratic function, but only to the left side of x equals 0. And I'm going to end it with a closed circle. Then I'm going to draw the piece x plus 1 between 0 and 2. So let's go ahead and put our dotted lines on 0, 2, and 5. So between 0 and 2 is where I'm going to graph the function x plus 1. So I'm going to start at 1 and then keep going up 1 over 1, up 1 over 1. Once I get to 2, I'm going to put an open circle. And if you noticed, I'm going to put an open circle starting at 1 as well on our x equals 0, and then connect my points. Then the last piece of the function is 5 minus x. So that means I'm going to start at 5, 1, 2, 3, 4, 5, and put a dot. And I'm going to keep going down 1 over 1 until I get to the pink line and put a closed circle. 1, 2, 3, 4. And then 1, 2, 3, 4, 5. I counted wrong the first time. Okay, down 1 over 1, down 1 over 1, get to the pink line, and I'm going to put it closed. If you notice, there's already an open circle there. My closed circle is going to overlap that closed circle. So now I'm going to keep going down 1 over 1 until I get to the other pink line and put a closed circle. Down 1 over 1, down 1 over 1. And connect my point. Okay, so the limit as x approaches 0 from the left side, that would be following here. My y value is 0. Then the limit as x approaches 0 from the right side, my y value is 1. So the limit as x approaches 0 does not exist, because from the left and the right, it's not the same. Then, as the limit as x approaches 2, because now we're going to look at the other part where the graph changes. From the left, we can follow that blue line, and we see that we get to the y value of 3. And then now from the right side, we again still get to that y value of 3. So the limit as x approaches 2, since it's the same for the left and right, the limit as x approaches 2 is 3. All right, let me know if you have any questions.